Section 3.5, derivatives as rates of change. Since derivatives are measuring slopes of tangents, derivatives tell us the rate of change, and we can say that because slopes are a rate of change. Slope is the change in y over the change in x. And so since slope is a rate of change on a graph, we can also apply derivatives as a rate of change to velocity problems and other applications. So we started off the chapter talking about velocity as an app, so we'll start there as our first application, applying the derivative now. So let s equal to f of t be the position function of an object moving along a line. The average velocity of the object over an interval from a to a plus delta t is the slope of the secant line. So average velocity would be f of a plus delta t minus f of a, so that's the change in position, divided by delta t, which is the change in time. So we're doing overall change in position divided by overall change in time over an interval, and that gives us average velocity. But as we look at that expression, if that delta t was an h, and if we took the limit as h went to 0 out front, then that would look an awful lot like the derivative of f at a. And that's no coincidence, because we talked about back in chapter 2 that if you take the limit as the difference between the 2 points goes to 0, you change from a secant line to a tangent line. What we know since then is that is called a derivative. So the instantaneous velocity at a is the slope of the tangent line to the position curve, which is the derivative of the position function. So instantaneous velocity we're going to call v of a, but that is going to be f prime of a. So it's going to be the derivative of the position function. Some other notations for that, since they said s was f of x or f of t, we can call it s prime. We could also call it ds dt. But the most important thing is recognizing that you get velocity by taking the derivative of the position function. All right, let's go ahead and try and apply that to an example. A state patrol station is located on a straight north-south freeway, and a patrol car leaves the station at 9 a.m. heading north with a position function s equal f of t that gives its location in miles t hours after 9 a.m. Assume s is positive when the car is north of the patrol station. And then we have a graph kind of showing us what was happening with this patrol car. And they want us to determine the average velocity of the car during the first 45 minutes of the trip. All right, so the first 45 minutes of the trip would be from here to 45 minutes. First of all, let's think about that. 45 minutes is 3/4 of an hour, because 45 minutes times, or over 1 times 1 hour equals 60 minutes. We get a cancellation of the minutes there, and then that leaves us with hours, but 45 over 60 is 0.75. So we're talking about 0.75 hours, which should be right here. So that's our ending point. So we know our starting and ending point, and they want us to get the average velocity. So we can do that by saying velocity average equals the ending position, which if you look at the height where we ended, or really the distance north of the station, was 30, minus where we started, which was a height of 0, divided by the change in time, which is 0.75. And then we'd also want to think about the units. It's 30 minus 0 miles, and on the bottom it was 0.75 hours. And 30 divided by 0.75, if you do the math on that, is 40, and 40 what? Miles per hour, because we have miles in the numerator and hours in the denominator. All right, so let's go ahead and look at a different one. Now they want us to look at a different time interval. So I'm going to go ahead and erase what we did before, and we'll set up a new one for the new interval. So they want us to go from 1/4 of an hour to 0.75. So here's 1/4 of an hour is right there, and 3/4 of an hour is where we were just a moment ago. And we want to find the slope of that secant line right there. Same math as before. So we'll just go ahead and repeat what we did a moment ago. We're going to do the change in position divided by the change in time. So we ended up 30 miles away from the station, and at a quarter hour, which was the start, we were 10 miles away from the station. We can see that right here. There's our 30 and our 10. So 30 minus 10 divided by the change in time, that was from 0.75 at the end minus 0.25 at the beginning. So we have 20 over 0.5, which if you divide that also turns out to be 40. So 40 miles per hour again, because again the position is measured in miles and the time is measured in hours. So we just found the average velocity, and then they want to know, is that average velocity a good estimate of the velocity at 9:30? Well, 9:30, that would be a half an hour after they left. So we'd want the slope of the tangent line right here. That secant line that we drew does actually look like a decent tangent line, so I would say for their second question, yes, because the secant line looks like a good tangent line as well. That's not always true, but it is here. All right, so now they want to know, when is the patrol car stopped? Well, if the patrol car is stopped, that means its velocity is 0, and that means the derivative is 0 of the position function. And we know that when the derivative is 0, we have horizontal tangents. So here's a spot that looks like that's happening, and down here is another spot where it looks like we're getting a horizontal tangent. So then the key is, they asked, when is that happening? So we want to get the value of t for that. So where are these peaks happening? This peak right here, if we drop down, looks like it's right in between 1 and 1 1/4. So maybe something like approximately t is 1.125 hours maybe. And then this other one going up from there looks like just a little bit before 2.75, so maybe that one's t is approximately 2.7 hours. So again, we're thinking about that application of motion like we did early on in the semester, but now we get to think about the stuff we know for derivatives. They want to know when the car is stopped. We know that's when the velocity is 0, but we also now know velocity is the derivative of position, so we're looking at where do we have those 0 derivatives, which is those horizontal tangent spots. All right, one final question to wrap this one up. Describe the motion of the patrol car relative to the station between 9 a.m. and noon. All right, so 9 a.m. to noon is the whole pathway. So what happens? We start at the station because our distance is 0. And then we're moving north because we're getting this positive distance. And then it looks like somewhere just after an hour, we stop, and then we start turning back towards the station. Maybe we go through like one of those U-turn areas for police officers in the middle of a freeway. And it looks like about 2 hours after we left, our distance from the patrol station is 0. So we went up north, looks like 35 miles, stopped, turned around, and now came back. We're at the station, but we didn't stop at the station because we don't have a horizontal tangent. We just drove by in the other direction and went, it looks like, somewhere in the neighborhood of like 27, 28 miles south of the station, and then turned around again and started heading back to the station. But by 3 p.m., it looks like we were not quite back to the station yet because we're still below 0. All right, so let's try and write all of that up. So the officer started at the station. And drove north because we have positive distance. And how long did they drive north? For a little over an hour, using our value from above for about 1.125 hours. Then they stopped and headed back to the station. and really headed back towards the station. But they didn't stop when they got back to the station. They drove by the station about 2 hours later, which I guess would be 11 a.m. And they went as far as like 28 miles south of the station. They turned around again. And then they started driving north again. So there's a lot of information in that graph. All right, so maybe we didn't need to say all that. Maybe we needed to say a little more, because I mentioned when I was talking, it looks like they went 35 miles north. So they drove north for about 1.125 hours, and it ended up 35 miles north of the station. The key thing really is to see that there's a lot of information on that graph that we can glean about which way they're going, when they stopped, like when they came back to the station, did they stop? No, because they didn't have the zero tangent there. So there's just a lot of information that can be garnered from a position graph, especially when you start understanding that the slopes of the tangent lines represent velocity. All right, let's go ahead and summarize what we were learning on the previous page. We're going to look at velocity, speed, and acceleration. Suppose an object is moving along a line with position s equal to f of t. Then the velocity at time t is the derivative of s with respect to t. So we could also say that it's f prime of t. And we would write velocity as v of t. So sometimes we talk about speed rather than velocity. And if we want to talk about speed, what we do is we take the absolute value of velocity. So the difference between speed and velocity is velocity can be negative. So like when that police officer was heading south, we would say they had a negative velocity because north was the positive direction. But somebody observing that patrol car coming south would just talk about its speed as 40 miles per hour or something like that. They probably wouldn't talk about it as negative 40. And then one we haven't talked about yet is acceleration. But acceleration is the rate of change of velocity with respect to time. So acceleration is the rate that velocity is changing with respect to time, which means it's the derivative of velocity with respect to time. So that's v prime of t. And remember that v of t is f prime of t, so the acceleration, if it's v prime, is also f double prime. All of those are ways that we could express the acceleration, which we would usually describe as a of t. So acceleration of a function is a of t is the way we write it. It's a rate of change of velocity with respect to time, so it's the derivative of velocity, which is the second derivative of position. So all of those things are related together. All right, let's go ahead and look at an example of a position function and explore some of those ideas. They're going to want us to graph it, and I went ahead and already set up the number lines on this graph. So if you want to pause the video and set those up, that would probably be a good idea. I'm going to just jump in and start doing the graph work. So consider the position function s equals f of t is negative t squared plus 4t minus 3. And we're looking at an object moving over a time interval from 0 to 5, and they want us to graph the function. So the first thing I want to do is think about, do I know what kind of function this is? And what really catches my attention is that there's a t squared, a t to the first, and a constant. And a function like that is a parabola. So if this is a parabola, I'd want to think about, does it open up? Does it open down? Where's its vertex? Where are its intersections with the axis? All those sorts of things. So we'll go ahead and start off with the vertex idea. So the vertex of a parabola, or the x-coordinate of the vertex of a parabola, is negative b over 2a, where b is the coefficient in front of the first degree term. So that would be negative 4, because there's this 4 in front of the t term, divided by 2a, where a is the number in front of the squared term, which in this case is negative 1. So the vertex is negative 4 over 2 times negative 1, which would be positive 2. So that's the x-coordinate of the vertex. If you want the y-coordinate of the vertex, you just have to plug in. So the y-coordinate would be f of 2, which would be negative of 2 squared plus 4 times 2 minus 3. And if you work all that through, let's see, we have a minus 4 and a plus 8, so that would be a positive 4 minus 3 is 1. So the vertex of the parabola is at 2, 1. And because the number in front of the x squared is negative, it opens down. And then you might also look for some other nice points on the curve. One nice point would be like, where does this object start? If you put 0 in, what happens? And if you go back here and you look at the initial function and you plug in a 0, what would happen? You'd get a 0 here and a 0 there, so you'd just get a negative 3. And then we can use a little bit of other knowledge about parabolas, which is that they have a symmetry to them. So if our y-intercept is a nice point and happened 2 units before the vertex, then another nice point should happen 2 units after the vertex at 4, and it should be symmetric, so it should be the same height, which would be negative 3. And you can plug in and verify that. But I'm going to just go ahead and plot all of these points that I have. So over 2 up 1 would be right here. We have over 0 down 3. And we have over 4 down 3. So we have a parabola. We know that from the type of function that we're dealing with. And then we know that we should have a horizontal tangent at the peak. And coming off that horizontal tangent, it's going to go to that point. And coming off from the other side, it's going to go to that point. So there's an initial graph, and then it would just keep continuing this way with a curve, and it looks like it would probably disappear off of our grid. All right, so there's the position function. Now let's find and graph the velocity function. So I'll go ahead and change my color here and start working in green, just so we can kind of tell the difference between the two. So if you want to graph the velocity function, the first thing you need is the velocity function. So the velocity function, v of t, would be f prime of t. And taking the derivative of that function, we'd get negative 2t plus 4. So that one's pretty nice and easy to graph because it's linear. So we could just make a table. If you plug a 0 in, you get out 4. And then if you plug a 2 in for x, you'd get negative 4 plus 4, which would be 0. So there's a couple nice points on the graph. Over 0, up 4. So that's right here. And then over 2 and down 0. And then draw as straight of a line through there as we can. If you happen to be on a tablet, you can cheat. Let it straighten it out for you. But there we go. So there is our velocity function. And then they want us to find and graph the acceleration function. So I guess we'll go to another color for that one too. Switch over to purple. So find and graph the acceleration function. So a of t is equal to v prime of t. So we have our velocity function right up above. So if we take this velocity function and take its derivative, that's going to be acceleration. And the derivative of negative 2t is negative 2. The derivative of the 4, since it's a constant, is just 0. So there's our acceleration function. So our acceleration function is just a horizontal line with a height of negative 2. So we can draw that one in right there. So there we have our position function in blue, our velocity function in green and our acceleration function in purple. And we can kind of study this like we did the police car a little bit too. So what's happening right here, the object is moving upward, and then during that whole stretch we do have a positive velocity while it moves upward. And then we reach a peak, which is a zero velocity, which we see on the intercept right there. And then we start going down, and during that whole downward point, our velocity is negative. And then as far as acceleration goes, that's constant, and that makes sense that the acceleration is constant if the velocity is a straight line. All right, so there's an example, and we will see some more on the next page. All right, let's go ahead and look at another example. A stone is thrown vertically into the air at an initial velocity of 96 feet per second, and the height of the stone in feet of the stone above the ground after t seconds is given by s equals 96t minus 16t squared. So the first question is, how high will the stone go? So what we need to realize about that question is, imagining the stone is thrown straight up and then it comes back down. So it goes up and it comes straight back down. So even if you just watch me draw that, there's a moment of pause at the top as I'm going up, and then I stop and I start to come back down. So in the same way, the stone is going to stop when it reaches its highest point. So what we want to do is come up with the velocity function, which would be the derivative of the height. And I guess they're not using h here, so we'll just say it would be s prime. And we're going to want to see when is that equal to 0. So first let's get velocity. So let's find velocity by taking s prime or ds dt, getting used to some of these different notations. And if we take the derivative of that function right there, which is our s function, derivative of the 96t is just 96, and the derivative of the minus 16t squared would bring down the 2, which gives us a 32 when we multiply with the 16, and then it becomes t to the first power. So there's our velocity function, and we want to know when is that equal to 0. So if we take it and set it equal to 0, then we can move the 32 over to the other side, get 96 equals 32t. We can divide both sides by 32, and that ends up going in nicely, and we just get t equals 3. So t equals 3 seconds is when this stone is going to reach its high point. But they didn't ask when that's going to happen. They asked, how high will it go? But if we know when it's going to happen, we can figure out how high it will go by plugging that 3 into the original function. So the s that we want, let me go ahead actually and switch colors since we switched topics, right? We were looking at the when, and now we're going to look at the how high. So s would be equal to 96 with that 3 plugged in, minus 16 with 3 plugged in again for the square spot, and whatever that is, that would be our height. And if you work out the math there, you get 144. And if you look back at the problem, it says that we're doing the height in feet. So this would be 144 feet, and that is our answer. So even though they asked us how high it would go, we had to answer a different question first, which is when would it reach its high point, and that would be when the velocity is 0. So we took a derivative, set it equal to 0, found that number, plugged it into the position function. So what do we have there? A 6-word question, but it brought about a lot of steps of work. All right, and then the next question is, when will the stone strike the ground and with what velocity? So when will the stone strike the ground? So if we did kind of a visual of that, we have the ground, we throw the stone up, it stops, it comes back down, and it hits. But when it hits, it's back down at the bottom again, back down to a height of 0. So the first thing we're going to do is set that height equal to 0. Not 5 equals 0, but s from our position function. So that would be 96t minus 16t squared equals 0. So we want to go ahead and solve that. And we can factor out a 16 and a t. That would leave a 6 and a t. So we have two places where this is equal to 0. One of them is when t is equal to 0, and the other one is when t equals to 6. So if you think about what those two times are, this first time, t equals 0, is when the stone left the ground. And this second one, t equals 6, is when it came back and hit the ground. So when will the stone hit the ground? It looks like 6 seconds after it's thrown. But they're saying, well, they did say when will it hit the ground, right? That is one of the questions. So we can answer that one. Say, when will it hit the ground? 6 seconds. So there's the answer to their first question. It's going to hit the ground after 6 seconds. Now let's move on to their second question, which is what's the velocity when it hits the ground? So we know when it hits the ground, and we have a velocity function right there, so we can plug into that, see what v of 6 is. V of 6 would be 96 minus 32 times 6. And if you do the math on that one, you get negative 96. And then what would the units be on that? So the units should be change in distance over change in time, and we're measuring the distance on this problem in feet and the time in seconds. So that would be the velocity with which it hits the ground. So what does the negative mean? Well, the negative means it was going downward when it hit the ground, which makes a lot of sense. Sometimes people say, well, if it's hit the ground, it's now stopped and its velocity is 0. That's after it hits the ground. The moment it hits the ground, it had some velocity to it, and then it stopped. All right, let's go ahead and look at another application. A 5-year projection of population trends suggests that t years after 2010, the population of a certain community will be p,000, where p of t is equal to negative 6t squared plus 12t plus 151. At what average rate will the population be growing between 2010 and 2012? So you could argue, like, we don't know how to do this. We've never done this type of problem, but it's still one we can do. They're asking for a change in population over a change in time. So what we want to do is figure out we want to find out the population in these two different years. We want to find the population in 2010 and 2012. So it could be tempting to plug 2010 and 2012 into the function, but notice that t is not the year. T is the number of years after 2010. So here in 2010, t equals 0. And here in 2012, that's 2 years after 2010, so there t is equal to 2. So what we want to do for the change in population is do p of 2 minus p of 0, and then the change in time is the 2 years that go by. You could also do it as the two different values of t, 2 minus 0. All right, to move forward, we need to know p of 2 and p of 0. P of 0 is actually pretty easy to do in our head. If you plug a 0 here and here, those terms go away and you just get 151. So this is going to be a minus 151 in the numerator. Let's see what the p of 2 is. We'll go to the calculator for that piece. So for p of 2, we want to plug into the function. So we have negative 6 times 2 squared. And then we have plus 12 times 2, and then plus 151. And it looks like actually, yeah, the negative 6 times 2 squared is negative 24. The plus 12 times 2 is positive 24. So those just cancel and you get 151. So interestingly enough, both of these numbers end up being 151. So we get 151 minus 151 over 2, which is 0. And so that's, what are the units on that? It would be 0,000 people per year. But what does that mean? That on average there was no change in population. Really, there was no change in population from the starting point 2010 to the ending point 2012. So the rate of change, the average rate of change, was 0. But it's interesting because if you plug a 1 in there, you don't get 151. So it's not that the population wasn't changing at all. It just happened to have been the same in both of those years. So let's look at what the rate will, at what rate will the population be growing in 2012? And is the population increasing or decreasing at that time? So they actually said it's growing, but I guess if it's growing at a negative rate, that would be decreasing. So at what rate in 2012? So now, when they say in 2012, that's not an average rate of change, that's an instantaneous rate of change. So just a little bit of notation. When we're doing average rate of change, we do delta P over delta T. When we want an instantaneous rate of change, we do dP over dt. And what we're saying there is we want the derivative of P with respect to T. So what we want is P prime of T. So P prime of T, since we just have a nice polynomial function, we can do the power rule. Negative 12T when we bring that 2 down, plus 12. So there is our instantaneous rate of change of population over time. We already talked about that 2012 is t equals 2. So now we just want to plug that 2 into our function. So we want to look at what is p prime of 2. That would be negative 12 times 2 plus 12. So it's negative 24 plus 12 is negative 12. And again, what's the rate of change there? Just like it was above, it's in thousands of people per year. So is the population increasing or is the population decreasing? Well, because the rate of change is negative, we would say that the population is decreasing. Sorry for running those together a little bit. So here's our answer to that second question. The population is decreasing. And here's our answer to that first question. The rate of change at 2012 is negative 12,000 people per year. Because it's negative, the population is decreasing. So notice we hadn't talked about this sort of application before, but now that we know that a derivative is a rate of change, you can do average rate of change like you do slope, change in y over change in x. Here we do change in p over change in t. When you want to make it an instantaneous rate of change of population, change that to a derivative, dp dt. All right, let's go ahead and look at one more example of the derivative as a rate of change. So after t weeks, a factory is producing n of t, 1,000 video game consoles, where n of t is equal to 2t over t squared plus 3t plus 12. Find n prime of 4, and what does it mean? All right, so finding n prime of 4 is going to be started by finding n prime of t. And then if you look at this, we have a numerator 2t, and we have a denominator t squared plus 3t plus 12. So what does that mean? It means we're going to use the quotient rule when we find the derivative. So we'd start off with the derivative of the numerator, which would be 2, times the denominator left alone. So t squared plus 3t plus 12. Then you would subtract the numerator left alone times the derivative of the denominator, or the green portion. So that would be 2t plus 3 using the power rule on that piece. And then all of that would be over the denominator squared. So t squared plus 3t plus 12 all squared. So there's n prime of t. Could we simplify that? Sure. Is that necessary? Not really, because they want n prime of 4, so we can just jump right in there and plug the number in and then simplify. So plugging in the 4, we get 4 squared plus 3 times 4 plus 12, in those parentheses, minus 2 times the 4, and then in parentheses 2 times 4 again, and plus 3. And then all of that over the denominator squared piece which would be 4 squared plus 3 times 4 plus 12, and all of that would be squared. So just going to work on that now. We have 2 times 16 plus 12 plus 12. We have a minus 8 times 8 plus 3, which is 11. And then all of that would be over 16 plus 12 plus 12. And then that 12 gets squared. So just working away on that, this 16 plus 12 part, that's 16 plus 24, so that's 40. So I end up with 2 times 40 minus 88. And on the bottom, we know that's a 40, so that's going to be a 40 squared. So it looks like we get 80 minus 88, which is negative 8, over 40 squared, which would be 1600. And 8 goes into 16 twice, so this simplifies down to negative 1 over 200. It said negative, but I didn't write it, so there we go. So there's n prime of 4, just as a number with no interpretation. And I normally wouldn't like to stop there. I'd think about what it means, but they're asking us to do that anyway, so I'll hold that off for down here below the line. So now let's address that question. What does it mean? So the easiest way to start thinking about what does n prime of 4 mean is to put the units on it. So it's negative 1 over 200, that's the number, but negative 1 what over 200 what? Well, this is a change in, what were we looking at? N was the thousands of video games and T was the weeks. So this is a change in video game consoles. So negative 1,000 game consoles over 200 weeks. And if you take that 1,000 right there and just make that a number, 1,000, then you can multiply it in and you can then do things like reduce. You can say this 200 goes into there 5 times, and by putting the number in, you can get rid of the word. So, and then that allows you to reduce. So now if we look at the reduced version of this, we have negative 5 game consoles per week. So now we've added the units, but we still want to really put it into a sentence. What does it mean? So it means that after 4 weeks, production is decreasing at a rate of 5 video game consoles per week. So let's go ahead and write that out, and then we will be done. So after 4 weeks, production is decreasing Again, we're saying decreasing because we have a negative slope. So after 4 weeks, production is decreasing at a rate of 5 video game consoles per week. If it had been a positive slope, production would be increasing. Since it's a negative slope or negative derivative, it's a decrease, so that's why we're talking about a decrease right there. And then we looked at the units to say that that's a rate of 5 video game consoles per week using the units that were provided in the problem. All right, that wraps up section 3.5.